So after you have seen the zooming of the Mandelbrot set, I will shortly explain what the Mandelbrot set is and then how to program something like this picture without the zooming for now, because that's a little bit more, I don't know, it's not that nice for a live coding session. But I'm sure you can figure it out how to do it. So yeah, here you can see the Mandelbrot set. So basically we have to work with complex numbers, and we have a series. So we have Z naught is the origin, and then the next Z is the previous Z squared plus our C, and the C is basically what we give as the starting point. So for each starting point on our plane, we use this series and check when it will diverge. So it will diverge if the absolute value of the Zn basically then is bigger than or equal or bigger than 2, because then it will grow forever. And then we have a different color scheme. So the color shows how long it takes to prove that it will diverge. And the black inside of the Mandelbrot set is it does not diverge. The black outside is we can immediately see that it diverges because it's bigger than 2 already. And the colors is something in between. And now I'll show you how to code something like this. Okay, let us start with the code. First of all, we will include images because we will later create an array where we define how many steps we took until we know for sure that we get out of the Mandelbrot set. That's what we include first, and then I can run that file already to precompile everything. We will need a function to get the number of steps. Okay. Oh, it's called colors. And that function we will get a complex number and the maximum number of steps we want to check. Then we have the z's, which will start at 0, 0. Or you can also write it like this. Then we will have z equals z plus our c. And if the absolute value of z is greater or equal to 2, then we can return I, and I will write it like this, so that we don't take the square root. That gives us a little bit, or is a little bit faster. And otherwise we return just one more. Then we have the function Mandelbrot plot, I would say, that will make it smaller at first, and then we can create the full HD video later on. Maybe 800. Maximum steps, like 50. Then we create an array which holds for every point, first y and then x. So for every point, the number of steps we took. So then we have to basically define first from where to where we want to do that. So I will call that CR min and CR max. Range for real values, range for imaginary values, CI min, max 1.2, and I will compute that with the height. Probably the range is CR max, CR min, and then we have dot size is range divided by width, and then we have CI max is CI min plus height dot size. Let's call that function and let's print out CR max. The same for CI. That is perfect. And okay, then we need a okay. Then we need a color map. I think I included color schemes already. And let me shortly, okay, check. I call it color scheme, and that will color schemes. And I will use Inferno. And oh yeah, then we also want to get, maybe do that a little bit later, so we can basically get okay, maybe first we create the image we want to save. So we want to save it into FileFormat. It's like this, I think. I use BMP here because it takes quite a while to convert it into PNG or JPEG, and it's much faster to save it like this. And then we can use color view, GB, and then colors, or like, yeah, let's call it image. And here we create the image, which is basically, not sure whether this works, probably not. What's wrong there? Okay. I think that process is a different one, so we can do something like this, and then we have a black image. And we could set like the first one to 1. And then we'll have a red image. Okay, perfect. And okay. Now this color scheme, we can use get color scheme max steps, and then take like step equals to 1. And we would get from 1 to max steps, and then we get a color out of it. So because we have this part and we want to have it black, I will get a get color function which takes in the color scheme and the step and max steps, and if a step is bigger than, or is max steps plus 1, then we return I think what's the best way? Yeah, I think we just have this 3-dimensional array which we had before. So we would return 0, 0, 0, and otherwise we return get color scheme step 1 to max steps. This is the actual color, and we return color R G E. Now we can actually iterate over the imaginary numbers first. Then we have dot size ci max. Then we get steps for our complex number, which is C is complex of CI, CR, CI, and max steps. We can okay, let's do it this way first. We do image and this is the black image first. It doesn't, we will set every color anyway, but we can then use y and x, and here we count up y and here we count up x. And okay, and then we also have get color scheme and max steps. And then we want to reduce this. This is because otherwise we jump over by one. So then we have this image, which looks quite nice. We can also move it a little bit to the right, maybe. So maybe have more like this. And we can increase the number of max steps, for example. It looks like this. Okay, let's let it be at 50. That is the first part. Okay, just for some might want to include benchmark tools and then include the road again, benchmark. No, I shouldn't. This runs it now a couple of times and we will get some benchmarking results, because this is probably not that fast. So this is 850 milliseconds. Okay. So what can we improve on? First of all, we can improve, and this is without saving, which actually in the end will take a lot of time. So the first thing we can do is, let's split this into steps. And have steps first. And we'll have this later. So this gives us the number of steps first. And then I think we should be able to do... Okay, that just way too long and didn't work in the end, so I'll just continue with another idea. Okay, what I think this part is actually slow, so we'll define our color scheme like a vector of colors, where we have get color that was a weird way. Okay, function get cmap needs a color scheme and it needs max steps. And then we'll have 4 max steps. colors. Colors is floats vector with 3. It's 1 because we have an extra color for the black one, and don't have this. This one will equal our black one again. You should write it like this. Can actually use our get color function here. Step and max steps. Let's see. What this gives us. We do like 5 steps. Okay, I promise this is the last edit for this video now. Oh, this is wrong. That should be I. Okay, yeah. Get that this part doesn't work. But sized. Oh, that of course should return our colors. And then we get back to 2 maybe, and then we have our 1, 2, and 3. Yes, and this is the last one. Okay, yeah. So these one are color because we have the 3 as the first dimension. Okay, and then we should be able to use image equal to color scheme. Steps. Yes. Perfect. That field faster. Somehow, I think. But, well, because we loaded that again. So we had 830 milliseconds before, something like that. Yeah, much better. Okay, and I think it's also quite a nice idea to have like the complex numbers in an array, and then we have complex, I'll just call it complexes. I'm not sure whether that's reasonable, of y and x equals to c. And we don't have this one anymore, but we can now get the steps of all complexes. Okay, we should first check whether it works, but no error is thrown, so that's quite good. Okay, that doesn't give us any speed up, but that's alright. I think it's easier to read. Oh, nope. Yeah, no changes there. Okay. And oh yeah, you can just do it like this. Okay, that's the first parts. So we have like 30 milliseconds now. And maybe to make it a little bit harder, we might want to zoom into something. I don't know, minus 1.2, and this is more like something like this. Maybe a bit more to the right, so like 4, 3, I don't know, something like this. Yeah, it looks good. And then we will do maybe 1,000 steps. Oh, I should load that first, otherwise we get wrong results. So later on we have to do more steps the closer we zoom in more. So this takes quite a long time now without saving the image, and we can also like measure the time every time we do it. And this is now saving the image. Okay, so now, because this is quite a repetitive task for every pixel, we have to do some calculation. Why not use the GPU for this? And then we create, we want to save the number of steps on the GPU, and the complex is the input. So we will do it like this. I think we can copy to. Oh, we have to define it first, but I think we can also do this. Let's check that. How do I define that again? I think it's just cool. Array of that's. Oh, maybe the problem is that we need to specify that one. Yeah, okay. And now we have that on the GPU, then we can have the steps can basically have steps on the, I'm not sure whether we have to do it like this. I think that will work. Is that we now do it like this, and then we have GPU arrays dot synchronize. It's GPU arrays, yeah, GPU arrays, don't synchronize. Do it for everyone, and then we have to copy it back. And that should be just array of CU steps. That might take a while first to have everything on the GPU running for the first time, compiling, stuff like that. Oh, we have to synchronize on something. Yeah, okay. Okay, that is faster now. Okay, you can see I thought there was a small spike for the GPU. But yeah, that's is already faster. And now, did we do a... Wait, do I have so much weird stuff in here now? Okay, because if we actually do it like this, okay, now you can see the GPU, of course, because we run it over and over again on the GPU. And now it took like 0.36 seconds, but here it's only 62 milliseconds. And this is only because we have to save the image somehow. And yeah, the next part would be just to iterate over it, change the CR min, CR max values, and CI min, and then compute CI max again, to zoom into one spot. And then let me copy something from here. And so we can just zoom in on something. Oh, please. And we have a black image. Nice. Okay. What if we do more steps? Now you can see something. So it's quite interesting that the color depends on the number of steps, of course. So I don't know what we had before, I think 1,000. So in the first 1,000 steps we can't decide whether it jumps out or not, and that's why everything was black. But if we increase the number of steps, everything gets brighter. So they actually do jump out, but at different points. And yeah, you have to be careful that if we use like 32-bit float values, that this doesn't work anymore with this basically range zoom level, because then it will be just, I don't know, 20 different values in float 32, and we have 32 different pixels or stuff like that, which would be quite bad. I think I can should be able to easily show you what I mean. Yeah, so it's basically just, they all look the same. So it's actually 1 pixel here. So let's go back to 64. Alright, that's it for today. Hope you enjoyed that one. See you next time. I want to thank my patrons on Patreon, especially those 3 mentioned here, because they pledge more than $4 per month, and they support my blog posts and the videos you see here. Additionally, I want to thank my anonymous friend here for the fractal background music. And here you can see some useful links I used, and I will also show them in the description. First of all, an Introduction to GPU Programming in Julia by Simon Danisch. And then This Equation Will Change How You See the World by Veritasium. And various Mandelbrot Set videos on Numberphile. I just picked, I think, the first one of them, where Dr. Holly Krieger explains the Mandelbrot Set. See you next time.